Hey everyone, today we're going to be talking about regularization. And to really understand regularization, the first thing you should look at is kind of the theory and philosophy behind it. So it comes from this idea of Occam's razor, or essentially in the data science sort of context, this idea if you have two different given models, the one that tends to be the simplest and the least complex tends to be better. And that tends to more generalize more to unseen data. Another way you can kind of interpret this is this idea that if you have a given model with a large number of parameters, like some of these really, really big neural networks that have hundreds of millions of parameters, and you don't feed it that much data, it's going to be very easy for it to find some combination of all those parameters in order to just literally memorize everything you give it, and it might not actually be learning anything useful. And so we'll talk about right now some examples of why you should care, even if you're running a simple linear model or a really large neural network, why you should care about using regularization for your own analytics. So this is actually a document that I made for my machine learning TA responsibilities when I was in graduate school. And so this idea, this has a pretty basic overview. Essentially, we're just going to make some random linear data with some noise. So this should just be best approximated by a very simple linear regression. And what we're going to actually do, though, is we're actually going to show how we're going to define some model. So maybe we thought that the model had 9 parameters, which each of these weights, and then some function, so like a polynomial model of our given inputs. And so once we run all this, and so we're going to generate some linear data into random. We have some training, testing, and validation splits. And I think the key here is to notice that we're only creating 8 of each sample. In other words, so now there's actually more parameters than we have sample sizes. And I'll show you why this is kind of a big issue, actually. And so we have just our simple loss function. We're going to go a little bit more into this in a second, but we have a loss function here. And essentially we want to say, we just want to minimize the least squares. It's just y equals mx plus b. What do we want to do? We want to take the predicted y from what that y actually is for every single point, sum it over. This is what the sigma means, summing over each of these points, and then square each thing. And the idea of the square is to actually make sure we actually get the absolute value or size of it, essentially. And so then, again, this is sort of what we're predicting as what our model y looks like. We actually know, again, it should just be a linear model, but we're going to predict like something like this. We'll see that if we do this because the key is we didn't have that many samples. And so this looks very strange, right? This should literally just be a line. This is essentially, we just made this data from a line with points, but it thinks that it's going to do some weird things like this. Why is that? Because it essentially found some combination. You can see another thing that regularization tends to do is it just kind of has really, really large absolute value coefficients, like 5,000, 5,700. And so this idea that essentially just found some random combination of these, really crazy looking weights and to perfectly fit this. You see how we have a training accuracy of 1. But if we actually try to apply this to, another data set, to the validations, really bad. So we only get 0.65. So again, we generated this data the exact same way using a linear model. But because we just defined our model in this way to have so many parameters, to have all these m's and this b, essentially it was able to just perfectly learn this. And so that's an issue. And so we'll go over a couple of ways actually how to fix this right now. So there's 2 kind of approaches that people have really thought about in ways to kind of address this idea of how to reduce the complexity of your models so that you don't necessarily overfit or train the data. And recall, even though I was mentioning the case that we did have more parameters than actual sample sizes, even if that isn't true, you can still have, a really big effect of this overfitting. So it's really important to kind of apply this really, if you're kind of doing anything related to kind of having a large amount of data or a very large model, you're probably going to want to look at doing some kind of regularization. Although also actually having a large amount of data would make you not need as much regularization. But the idea of there's kind of 2 different ways that people directly control regularization. And so this idea that you can either enforce this kind of sparsity, and this is kind of an example given in the L1 or lasso, which we're going to go into more. This is least absolute shrinkage and selection operator. And we also, in addition to having sparsity, in other words, so like this is useful for genes because some genes, like if you have a given drug, that drug might interact with some genes, but not all of them. A very few selection, you just want a 1 where on the genes that it interacts with and a 0 everywhere else. So this idea, it's very sparse. You have solutions that you have a lot of zeros, but you have, just a 1 or a couple of samples that actually, or a couple of features that actually have some weight attached to them. So it kind of affects the complexity by shrinking a lot of the unnecessary features down to 0. In contrast, you could also do something similar to size of coefficients, essentially just shrinking the overall size. And they actually both kind of do both of the, although L2 won't ever shrink anything down to all the way. but they both kind of enforce this idea. And so these are just kind of general ideas of how people actually, affect the complexity of models. So let's take a look more at how specifically the math works out for these. So this is a lot of kind of complex math, and I tried to write this in a way that could just communicate exactly what I was trying to say. But just starting from this idea that we're starting, with the basic y equals mx plus b, right? So we want to find a linear regression. We want to find essentially an m and a b. And the idea of what the m and b, we essentially want to minimize this distance with respect to y hat. So we want to say, for every data point, what's the distance from the predicted value of this m and b? What are the values of m and b that actually give me the y that when I add them up for all the samples, remember this means adding every sample up, when I add them up for every sample, we're actually able to minimize this distance. And so this is kind of what you might have seen before. You probably did a couple of these maybe in high school math or undergrad math. And so this idea that you can do this regression, but this is sort of the unregularized regression, right? So if we have a very complex model for this y hat like we had before, essentially just doing this would kind of give us just crazy solutions like we had before, and we really need to figure out a way to do this. So what we essentially do is we're going to essentially add this term to our regression. So this is kind of all complex, but just stay with me. I think we can get this taken care of. And so this idea, you multiply some lambda by the absolute value of all your weights combined. So you essentially sum up all the absolute values. And so this is sort of shrinking each of the coefficients, right? Because you're saying, well, now I want to minimize not only just this term that represents, the distance between the y and y squared, but I also, in addition to that, I also want to have this term that minimizes each of the m and b's, each of the features. There's another way of, writing this for however many features you need. And so this idea is, this is, you can see how this would be the L1. This would actually say, well, if B was not important at all, we could just shrink that down to 0. That could be completely 0. And then that would, minimize this a lot better. So this idea of this version using this absolute value on these weights is one way of regularizing. And the next way we look at that is actually the exact same way, but just at the very end, instead of using the absolute value, they actually use the square of these weights. So these weights squared, some of these are still, this is still a way of getting sort of this absolute value. It's a little bit different than absolute value though. So I want to actually shrink everything to 0, but the sort of philosophy kind of stays the same behind both the L2 and the L1. And the idea is that you essentially take your loss function and you want to add some term that penalizes based on the size of your weight. You see, so now if the m and b are very high, this is more difficult to minimize. And if you can kind of get that, that's essentially the idea of regularization, or at least explicit regularization. And so we'll talk a little bit more about this maybe when I go into regression, but now I'm going to talk about some other kind of things that you'll see if you look more into regression. So you might have noticed, and maybe was wondering what that lambda was before. So that lambda that was multiplying the weights out is essentially just a tunable parameter that your model needs to learn. And it's essentially a balance between, obviously, if you, maybe not so obvious, but if you increase this lambda, if you look back at the other formulas, you're essentially increasing the weight on that regularization term. You're essentially saying that you want to penalize those coefficients more, the absolute size of those coefficients. So that actually prevents overfitting, but it does actually make it harder to learn your problem. So sometimes this can be so high that you actually are not able to learn anything. In contrast, you can think about how the opposite would be if you actually lowered this lambda, you'd have less regularization effect. But it's so you can actually, learn from your data, but you're more likely to just memorize that data and overfit. So you need to actually look at, usually try a different couple types. You can use cross-validation to find this. And so this idea that you need to, you need to have some justification for choosing this. That just depends on your data and your model selection. So we're going to try to do the same model that we had done before. We're going to see what happens if we actually apply this regularization. You can get all this code. I'll have posted in my GitHub. You can feel free to modify it and do whatever you want with it. And so this idea that essentially we'll try to just run this part. And so this was actually an L2 regularization with a lambda of 1. And so you see how now this looks a lot more reasonable. This is literally just so it kind of smooths it out. I think really important to notice that these are all, look how small these coefficients are compared to them to the previous coefficients. The other ones were like 5,000. These are less than 1. And so this idea of essentially we're able to shrink these coefficients. And all the training accuracy, remember the first training accuracy said it was 1, but that didn't really generalize well. This training accuracy says it's 0.861. And so we're going to try this again with another model. This is for with a smaller smaller lambda, so 0.05, and this is one actually, so we're still regularizing, but not as much. And so you can still see that these are kind of larger, but still not as large as the previous ones. But our training accuracy is 0.971. Everything seems to look good. So what we're going to do is we're going to first look at, if we recall, these are our training accuracies. And so we want to really just kind of compare this, and we want to, so we have, let's say we have this in a real situation. We say, well, what actual lambda do we want to use for these? And so what model should we use? We should look at the validation set for that. And so this is our validation accuracy. It looks like the one with the 0.05. Which is usually what happens, as I already have it here. But this kind of model tends to have the highest accuracy on this unseen set. So we expect this model to actually have the best one, which it does on the testing accuracy. So we see that we were able to actually determine which one of these without. If we had just gone to the testing accuracy, that has the risk of overfitting. And so the idea that we're tuning our lambda based on our validation to actually find our testing accuracy. And so this regularization actually allowed us, one of the things you can do is, you can have this really complicated regression model. And this is why I was talking about the case of genes, where you could have every single gene in the body. There's at least thousands and thousands, right? And so you don't need thousands and thousands of people. If you apply some regularization to it, you can actually just still get informative things from using this sort of regularization effect. And so just to talk one more time a little bit about the lasso. And so this one probably might have actually been better. But if you notice, so essentially it shrunk a lot of these unnecessary coefficients down to 0 entirely, as we would expect with the lasso. So they this one focused on the sparsity constraint, and still just gives us a good model. So again, you probably want to compare all the lasso regressions and the hinge one and the ridge ones to each other. So now I really want to communicate exactly what this idea of regularization kind of extends beyond just adding concrete elements to your loss functions. And so this idea that there are these you could do things in regression like we just saw, you can also do things in neural networks. You also have this idea of this implicit regularization effect. And there's also, so it's essentially you're doing things that control for overfitting, but you're not actually directly adding things to your loss function. You're doing that in other kind of ways. And then also finally, they've been some research that shows essentially, these are essentially just the equivalent. Regularization is equivalent to just having a Bayesian prior on your coefficients, and essentially you're penalizing it based on distance from having a simple sort of structure. So there's actually some equivalence to Bayesian interpretation. So there is really big field. Honestly, you could teach a whole class on regression, and I think that there's a lot of exciting things that will come up. So we're just going to talk about, what else is. So I think that the most common things, if you really understand the L1 and the L2 regularizations, I think you have a pretty solid grasp, and I think that you can start thinking about that. But also, looking beyond that is not just regression, but you can apply these sort of direct L2 weight penalties to neural networks. But I really want to, I think for this slide, you see that there's a lot of different work being done in this sort of implicit regularization effect. And this idea is that you can do other things in your models that may not be, directly attributable to actually, decreasing overfitting through the loss function, but they're actually, very helpful for doing that essentially. And so these are examples. And so if you don't know too much about these, I'll go more about these when I talk about neural networks, but things like dropout and stochastic gradient descent have been shown to have this sort of implicit regularization effect, and that doing these sort of methods actually improves or decreases overfitting on the other sets, so that they end up being sort of good. So even though they're not directly applied to the loss function, it's really does have this effect that essentially is like a regularization like effect. And so summary, it's like regularization really is just anything that is used to prevent overfitting in the data science context, and it can be explicit or implicit. Hey guys, thank you so much for watching. I'll leave you with one more example of a sparse data structure. Is definitely how many subscribes and likes I get. There are a lot more views than subscribes and likes. They really help out the algorithm. They would really help me out. If you're interested in learning more deep learning content, leave a comment below if there's anything you want me to go over. Feel free to ask me anything on either Reddit or YouTube. Thanks, bye.